Hello everyone. Today we're going to be doing a quick video presentation on tuning controller gains in scanning probe microscopy, which is a topic central to achieving stable, high-resolution surface images. So what exactly is scanning probe microscopy, or SPM? It is a family of techniques that scans a sharp tip across a surface to gather nanoscale data. Two core types that we're going to be talking about here in further detail is STM, which uses tunneling current, and AFM, which measures interatomic forces. Both rely on precise feedback and control systems to maintain stability during scanning. Just for reference, here are a few of the other SPM techniques. The first method we are going to be talking about here is STM, or scanning tunneling microscopy, which was developed in 1981 as the first SPM technique. It uses a conductive tip placed within 1 nanometer of a surface, allowing electrons to quantum tunnel between them. The tunneling current is exponentially sensitive to distance, which is why precise control of the tip height is so critical. Here we can look at some of STM's key components, which includes a metallic tip, a current amplifier, and a PID feedback system that keeps current constant by adjusting the tip height. STM modes include constant current, constant height, and even atom manipulation in advanced setups. The other SPM method we're focusing on, AFM, or atomic force microscopy, was introduced in 1986, a little after the STM. It scans both conductive and non-conductive surfaces by measuring the forces between a sharp tip and sample surface, typically via a deflecting cantilever. Now, here are some of AFM's key components and modes, which includes a cantilever with a nanoscale tip, a laser and photodiode to detect bending, a piezoelectric scanner, and a PID controller to maintain stable interaction. Modes include contact, non-contact, tapping, pinpoint, and more, each with unique control demands. Earlier, we mentioned tuning controller gains, but what exactly is a gain? In control systems, a gain is just a multiplier that determines how strongly the system responds to error. If your system is lagging, increase the gain. If it's oscillating or unstable, the gain may be too high. Tuning gains correctly is what makes feedback systems effective. Also mentioned earlier was control systems. So what exactly is the role of control systems? Well, control systems are the backbone of any SPM operation. They maintain constant interaction forces, adjust the tip height in real time, make high-resolution imaging possible, and more. Without them, the tip would either crash or float, and image data would be unreliable. Some of the most important control components include the cantilever tuning module, which detects resonance frequency, the Z piezo actuator, which adjusts vertical tip position with nanometer precision, and the lock-in amplifier, LIA, which extracts clean amplitude or phase signals from noisy input in dynamic AFM modes. Generally, when we think of control systems, we think of something scary, like this block diagram. But for now, we can simplify that. This block diagram, which is based off of a PID control system, is a little bit friendlier to start with. One of the most fundamental control systems is the PID controller. The PID controller is the core of the feedback loop. It consists of three terms: P, which reacts to how big the error is and stands for proportional; I, which accumulates long-term error and stands for integral; and D, which responds to how fast the error is changing and stands for derivative. Together, they calculate the voltage needed to move the tip appropriately. For PID controllers in AFM and STM techniques, manual tuning of gains is standard. The common method is to increase P until the system becomes unstable, then back off slightly and slowly add I. This approach is inspired by the Ziegler-Nichols method, but avoids intentionally destabilizing the system. The D term is usually left at 0 to avoid amplifying noise. Presented here is a means to visualize the PID response graphically for every piece of the controller. PID controls try to mitigate the off-target approach of the machine in question to reach a user-defined set point. P immediately responds to the error. I corrects accumulated drift from the set point, and D can dampen rapid change, leading to faster corrections. Moving on to more specifics, in STM, the PID controller adjusts Z height to maintain constant tunneling current. Since current is exponentially sensitive to distance, stable tuning is essential for atomic scale imaging. Constant current mode is the most common and entirely dependent on this feedback loop. For PIDs in AFM, in contact mode, the controller maintains constant deflection, while in tapping mode, it maintains constant oscillation amplitude. Tuning typically begins with just P, then adds I for drift correction. D is avoided, especially in tapping mode, because it amplifies system noise. Now, let's talk about the results of tuning. It's important to highlight that tuning quality directly impacts image quality. If gains are too low, the system lags and fine surface features blur. If gains are too high, you get oscillations, unstable feedback, or even damage. Properly tuned gains lead to stable, high-resolution, artifact-free images. Moving forward, here are a few tips to make sure that you have a high-quality image. Avoid overly high eye gain, which can cause creep or slow oscillations. Always tune with your specific sample and scan mode in mind. Finally, control for temperature and vibrations, which can shift your tuning performance. To summarize everything, SPM systems like AFM and STM rely on PID controls to maintain precise tip-sample interaction during scanning. Manual tuning of PID gains, especially adjusting P and I, is standard practice, tailored to each sample and scan mode. Improper tuning leads to noise, lag, or instability, while well-tuned gains enable clear, high-resolution imaging. Ultimately, successful tuning combines control logic, system hardware, and operator judgment. Thank you for your attention on how controller tuning shapes the performance of scanning probe microscopes. If you have any questions, leave them in the comments below, and my resources are posted here. Thank you.